Hello, we're going to do a little video here. This one's actually going to go a little on the longer side, so if you feel like you need a break, go ahead and hit that pause button, take a couple and come on back. But this may also be one of the more important videos you watch. It's going to be critical to help you on assignment 1. We will have some opportunities within the classroom setting to visit some of these issues should you desire, but this is going to be a great thing to watch once quite thoroughly and then review especially the last few slides as you get going on your homework. And the topic here is sun angles. And so we're going to talk about first and foremost what exactly is a sun angle. And you may have some feeling for this already. It's August, it feels like the sun's high in the sky, but those of us that live in the mid-latitudes know that that angle is going to be pretty low within a few months as we get into October, November, December, and we're going to discuss how this relates to the seasons. And it's also going to have strong relationships with energy, how much energy is actually making it to the top of the atmosphere, and then theoretically how much of that can make it down to Earth's surface depending on clouds and some of the other properties that we've learned about within the atmosphere that are going to influence how much energy makes it to Earth's surface. What relationships exist between sun angles and weather? Some of it is going to be quite simple, whether or not you're going to be warm enough for rain or cold enough to snow. And why should we care? The recurring theme that I bring up, including thinking about what is your favorite season and what are the sun angles like during that season of choice. So a few facts about Earth to kind of get us moving on the right track. It moves pretty quickly. Thankfully, we are within Earth's system, so we don't feel that rotation. Otherwise, many of us would probably feel a little on the ill side, but it's moving fast. It revolves around the sun once every 365 and 1/4 days, thus the need for the leap year. It rotates on its axis once every 24 hours, and that's why we have 24 hours as the period of which is 1 day. The orbit of Earth is slightly elliptical. It's not exactly circular, and we refer to this as its eccentric, so just a little outside the norm. The word is eccentricity, and this will come up a little more regularly when we get into some climate stuff later in the semester, that Earth is not necessarily moving the way we all realize. It's just that the period at which some of these changes occur is on tens of thousands of years. It's actually closest to the sun in our winter here in the northern hemisphere at about 147 million kilometers, and it's farthest away in our summer, about 5 million kilometer difference. But this brings up the idea of why are we warmer in July than we are in January? And that's going to be related to that idea of sun angles. Another theme that will come up regularly in this class is the idea that we have so much more landmass in the northern hemisphere than we do in the southern hemisphere, and that also plays a role in why we don't see significant differences on a global scale between January and July. And finally, one of the things that is very important, but to be fair also makes this a little more difficult to fully comprehend, is the idea that Earth's axis is slightly tilted. It is critical in understanding why seasons exist. What seasons are we tilted towards the sun, and what seasons are we tilted away from the sun? Understanding that these are going to be different depending on which hemisphere, northern or southern, you live in within the world. So again, the eccentric path of Earth. This makes it look like it's a big oval. In reality, it's just the way the diagram is shown. But you can see again here a little closer to Earth in January when the southern hemisphere is tilted towards the sun, and a little further away in July when the northern hemisphere is tilted towards the sun. And so what you can grasp from this graphic is the idea that the tilt is actually going to be much more critical than that 5 million kilometer difference that occurs between January and July. Earth's revolution. Here we can see a number of things that are going to become quite common in terms that you absolutely should get comfortable with. The equinoxes at the top and the bottom of this image. The autumnal or autumn equinox. Fall equinox is oftentimes the term in which is used. And then the vernal equinox or the spring equinox. Those are going to be times equinox equal. All points on Earth are receiving 12 hours of sun on these dates. Because of that 23.5 degree tilt, the summer solstice, June 21st, is when the Tropic of Cancer in the northern hemisphere at 23.5 degrees north is where the sun is directly overhead, and the Tropic of Capricorn, or 23.5 degrees south, is what is directly where the sun is directly overhead on the winter solstice. And so if you've always wondered what day around here, say the Midwest, whether you're from Chicago, Valpo, or East Coast, New York City, San Francisco on the West Coast, you're going to get the most daylight on June 21st and the least daylight on December 21st. So even though we're quite warm outside, and it's not necessarily a time of the year that you'd expect to be cold, we're well past when we have the longest day. In fact, here in Valpo, our sunsets are already occurring prior to 8 p.m. local time. Another factor related to sun angle is going to be how much of that sun angle is reaching Earth's surface. This is going to kind of come in with some mathematical equations by the end of this lecture. One thing that's really important to grasp is the idea that a high sun, or one that is directly overhead, is going to create a more concentrated solar beam. It's going to have less of the atmosphere to traverse, and so if we think back to what can happen to that solar energy, whether it's absorbed, whether it's reflected back by cloud tops, scattered away, less atmosphere between the sun beam and the Earth occurs when the sun is high in the sky. And so here, the angle here with the high sun and the low sun, we show with flashlights on the left side of the image, and I strongly encourage you to give this a try, and we'll try to do it in class as well. If you take a flashlight and put it over just part of your desk, and don't actually lift it or move it to a greater distance away from your desk, just give it a little tilt. It's still emitting the same amount of energy, the same amount of light is being produced, but it's going to make it more dim and diffuse on your paper or on your desk surface. And that means that points on the Earth that are at a low sun angle are getting less of that solar energy, making it down to Earth's surface. And so the length of daylight, more daylight equals more energy, but the concentration of that energy is also critical. We'll note later on that there's points way up towards the poles, both in the northern and southern hemisphere. They're going to have periods where there are 24 hours of daylight. It doesn't necessarily mean that they're getting hot, though, because of this sun angle. It's still a relatively low angle. And so if we look at the northern hemisphere, what's in the green box here is important. Thus the reason it says, important to note that more hours of daylight does not automatically equate to more solar energy reaching Earth's surface. This is particularly true as you get into what's known as the high latitudes, or areas towards the poles. Here in this example on June 21st, or your summer solstice, you are getting an area north of the Arctic Circle that is receiving 24 hours of daylight. If you've ever heard of Alaska termed the land of the midnight sun, this is why. There are periods north of 66.5 degrees north that see much more than one day where the sun doesn't set. They see months where the sun doesn't set in some areas. But because that beam is at a lower angle, it's more diffuse, and it's not necessarily having the potential to warm as well as you might have at lower latitudes. In this example, you can see the beam directly overhead at 23.5 degrees north. So even though areas here, say across Mexico or the Caribbean, are receiving only 13.5 hours of sun in the day, that concentration is going to mean more solar energy reaches Earth's surface. And because of both that fact and the prolonged period in which they get more sun, is going to mean conditions near the equatorial regions are in general warmer. All right, let's get a little bit more about these terms. And these are terms that you absolutely should be comfortable with before the first exam. Summer solstice, first day of summer in the northern hemisphere. We have these relationships to the sun to define our seasons, which are slightly different than what we often use for the terms meteorological summer or meteorological winter. But technically speaking, the first day of summer in the northern hemisphere occurs right here around June 21st. This is when the sun is directly overhead at the Tropic of Cancer, 23.5 degrees north latitude. Flip it, switch it, reverse it. When it is the first day of winter in the northern hemisphere, corresponds to the first day of summer in the southern hemisphere. And so in the land down under, Australia, you're getting pretty warm. The sun is directly overhead at the Tropic of Capricorn, or 23.5 degrees south latitude. This is going to occur on December 21st, so here in Valpo, the lowest number of hours of daylight is going to occur on that date. So if you're not a fan of winter and you like the sun, realize that by the time we've hit the Christmas holiday here, at least in a normal year in Valpo, we're already starting to increase the number of hours of daylight, even into January and February, which, if you're from anywhere around here, you know can be quite chilly. March 20th, September 22nd, or very, very close to it, are also important days. These are what are known as the equinoxes. Again, oftentimes called the spring and the fall equinox. And these are going to be when the sun is directly overhead at the equator. What is neat about the equinox is that means there is 12 hours of daylight occurring everywhere on Earth's surface. Whether or not you are in Buenos Aires or Tokyo, Chicago, Valpo, Tampa, Honolulu, 12 hours of daylight. That does not mean the sun angle, however, is the same at each point because you're getting it directly overhead at the equator, whereas it's actually a pretty low angle still here, in the Valpo, Chicago metroplex. And so this is a graphic that you may wish to take a couple of moments and think about. If you'll notice in the middle of each image, there's a silhouette of a human being. And so here in A, you can see that as you work your way towards the winter months, the sun is below the horizon. You would not see any sun at all. But when you're at June, it's high in the, or it's not high in the sky, it's low in the sky, but it is going to be visible 24 hours a day. And so at the North Pole, once you pass March 22nd or the equinox, we're going to start to see that sun very, very low in the sky, but prevalent throughout the day. But between the fall equinox and the spring equinox, the sun does not rise at the North Pole. Arctic Circle, we can see that it goes all the way down to the horizon as we get towards December, creeping up to where June it's going to be up for 24 hours on that one exact day at our summer solstice, but still pretty low sun angle. Part C, the middle latitudes, here is a good example of Valpo. Here at Valpo, we're at about 41 degrees north latitude. And so in June, a lot of hours of daylight and a pretty high sun angle. At the equinox, we're getting that 12 hours of sun at a lower angle. And finally, in winter, a lot less hours of daylight and at a much lower sun angle. Again, think of how this viewer right in the middle would see a December sun on the horizon versus a sun at the equinox versus the sun that seems like it's almost directly overhead in June. And then if you work your way down towards the Tropic of Cancer, here this would be when the sun is directly overhead on the summer solstice, so we get a lot of hours of sun directly overhead. Equinox, 12 hours, still a high sun angle, and even in December, because we're closer to the equator, not that far away from 23.5 degrees south, we still get a decent amount of hours of sun and at a reasonable sun angle. Equator, 12 hours of sun, slightly different angles depending on where the sun is at overhead on a given date. And then the Tropic of Capricorn is basically the Tropic of Cancer and just reversed. Again, this may take you a little while to sort through and get a feel for it, and you may need to watch this portion of the video a couple times. That is normal and encouraged. Again, at the equinoxes, we're getting 12 hours of daylight at every latitude, but if you start to envision all of these yellow arrows as flashlights, you can see that it would be concentrated directly overhead the equator. Much lower sun angle if you were to have a plane that is going to be perpendicular to Earth's surface here at, say, about 40 degrees north latitude, or Valpo. And then as you get up towards the North Pole, effectively a sun angle of 0 at this date. Looking at the winter solstice, this would be December 21st, when we have the sun directly overhead at the Tropic of Capricorn. And you're going to see that on this date, you have areas that are experiencing 6 months of daylight at the southern pole, all the way to 6 months of night at the North Pole. So you win some and you lose some, to be fair. Here around Valpo, maybe about 9 to 10 hours of daylight. But as you get down towards the southern hemisphere, you get an increasing amount of daylight. And especially here, you're getting a relatively high sun angle where it's directly overhead at 23.5 degrees south. And so let's focus in on this band right here, 40 degrees latitude. 12 hours of sun we would be receiving on March 20th as well as September 22nd, those equinoxes. And the variance recurring between a low of around 9 hours and a peak of around 15 hours. Again, that's pretty relative here at Valpo. What you can see is that when you're at low latitudes or near the equators, not much variance. Mid-latitudes, some variance, but not crazy amounts. And as you work your way up towards the Arctic Circle, we're getting significant change throughout the course of the year. All right, so let's talk about the idea of actually calculating, or what is this sun angle? And so we're going to try to do the demo with a globe one of these days in class, turn out the lights and kind of get a feel for how that is. And so if we talk about sun angle, we're talking about the angle of the sun relative to the horizon. And so picture yourself standing outside, looking out on the horizon, and it would be a 0 degree sun angle if the sun were literally looked like it was on the edge of the earth. And if you look directly up in the sky, if it were overhead, we would refer to that as a 90 degree and most intense sun angle. And so it's going to be this angle that we're working with right in here. High sun angle directly overhead, moderate sun angle being shown in here, which is leading to a more diffuse beam. And as this angle becomes smaller and smaller and smaller, our sun angle becomes lower and lower and lower, and we're getting less of that down to Earth's surface. They try their best in this schematic to show you palm trees versus pine trees. And so this slide right here is one that you will almost certainly want to revisit on a couple of occasions. We will go over it in class if it would be helpful, and you may also ask questions when you're in your lab settings in the upcoming weeks before this lab is due. And so here when we talk about calculating the sun angle, we're going to be concerned with two critical pieces of information. First, where are you, or where is the point of interest? And so in this example, pretty close to Valpo, we're saying that our location is 40 degrees north latitude. The other critical piece of information is where is the sun directly overhead on a given date. And so in this example, the date is December 22nd. Notice there's a little variability here between 21st and 22nd, but regardless, we're going to treat this as the winter solstice. And we're going to say, or then, let me rephrase that. Therefore, we know that the location of where the sun is directly overhead, here referred to as the 90 degree sun, is 23.5 degrees south latitude. It is imperative that you are keeping track of north versus south latitude. It may help you to draw a little figure where the location is that the person or the location of interest is, and the location that the sun is directly overhead, so you start to be able to grasp how much distance is in between those locations. And so to actually calculate sun angle, it is pretty simple. You know where you are, you know where the sun is. And so we calculate this difference in the degrees between where the sun is directly overhead, here 23.5 degrees south, and where you are located, here 40 degrees north. The difference between these two locations ends up being 63.5 degrees. The second step is as easy as it gets. Take 90 and subtract the distance in degrees between where the sun is overhead and your location, here 63.5, and that provides you the noon sun angle at your location on a given date. Here, 90 minus 63.5 leaves you with 26.5. And so if you again consider a plane that is perpendicular to Earth's surface at one given point, the sun is directly overhead here on the Tropic of Capricorn, but it is much lower angle here at 40 degrees north. That leaves us with that small, in fact, if I go back up a slide, a very small value here, not 45, but down to 26.5 degrees. Low sun angles mean the sun is down towards the horizon. High sun angles means that it is nearly directly overhead. Again, feel free to refer back to this and we can talk about it in class. Note that this slide has a typo in the schematic, not my fault. That should say 23.5 degrees south. And so the last step here is sometimes we want to know how much of that sun is received at the top of the atmosphere at these different sun angles. And so here we have our solar constant, 1368 watts per meter squared. If for some reason you've chosen to view this video and not an earlier one, you may want to review a little bit about the solar constant. But if we have our 1368 watts per meter squared, we want to know how much of that is being received given the sun angle at hand. And so in the previous example, we had a sun angle of 26.5 degrees. If we know that sun angle, This looks like a very complicated equation, but in reality, it's not. I is simply the solar radiation that is actually received at the top of the atmosphere. And I naught, which is this I sub 0, we usually call it I naught, is going to simply be a constant. It's always 1368 watts per meter squared. Yes, your book has a slightly different value. No, it's not that important to know the difference between the two. Simply use 1368 for simplicity. So, to calculate how much solar radiation is received at the top of the atmosphere, we plug in 1368 watts per square meter times the sine of our sun angle. So if we were to plug that in, you would simply take the sine of 26.5 degrees, multiply that by 1368, and that will give you your value for solar radiation at the top of the atmosphere. And so you'll notice that as your sun angle approaches 90, you should get some values for I that, make sense. Whereas if you have a sun that is below the horizon, you should realize that this is probably going to be 0. Final help here is if for some reason you're not getting values, check your calculator settings, whether or not you're utilizing your phone, whether or not you're using your TI-80 whatever. Make sure that your values are set to degrees and not radians. You will not get good answers if things are set to radians. Again, this is going to be part of the homework assignment, and we can revisit this as needed as well. All right, you made it through sun angles. This is admittedly one of the tougher topics over the course of the semester. It is one that I think works very well in video form, so review portions of it as needed. We can address it as much as is required in class, and then take some time before lab this upcoming week, and that will also allow you the opportunity to ask some questions about the homework or the assignment after you've completed the week's lab. All right, that's all for this one. Again, went about 22 minutes, so hopefully you made it through. Otherwise, go back and review as needed. Have a good one.